2, 1. All right, okay, so this is the last test that I'll do, I guess, for grade 11. And it's on sequences and series. So just as usual, you can find in the show notes the download link to the test. Try it out, come back and see what it goes. Now, for this test, okay, so we will be utilizing, the arithmetic and the geometric series. You will also, should know a little bit about Fibonacci sequence. So for that, and I'll try to tie it into simple and compound interest, just a touch through the last couple of examples, and then I'll post the entire lists for those simple and compound interest as well on the 1mjourney.com. Okay, so under Learn in High School. So one thing that you will need, most students kind of memorize these. So these particular equations for arithmetic and geometric, so both for the sequence and then the summation for the series. I forget them, to be honest, and I sometimes, I'll teach it, and if you're not doing it for a while as a student or even as a teacher, prof, whoever, you probably will forget. So I like to derive them always from scratch, so I always kind of like remembering the little trick that I use for deriving. And if you don't remember, I'll put up a playlist up above to the whole entire sequence series. If you hit the playlist, then you can go to whichever one, and I derive these formulas there for you. Okay, so you can have them. So we're going to be using them in this particular test. Okay, so let's knock it off. Okay, so question number 1. So let me copy this down. I'll bring it down below. So let's paste it and let's see. Okay, so how we're going to try to solve these. Take the following arithmetic sequence. So we have -11, and then I guess it continues on into -92. We're going to assume the sum of the sequences. Okay, so they give us the sum. All right, let's just write it down. So I guess, what do we have? We have T1, so our term number 1, which is -11. We have term number n, I guess that's -92. We have the sum of all of the entire thing, which is -1442. That doesn't give us enough, I guess, but find how many terms there are. So we're supposed to find n. And the sequence has and the arithmetic difference between each. Okay, so it's an arithmetic sequence. So, I mean, that's good, because that means we can utilize these two things right here if necessary. So I'm going to bring these down in here. Let's see which ones we'll need. Copy, paste. All right, so I'll use that. So we want to know how many terms and what is the difference. All right, so what is the difference between them? So it looks like it's decreasing, so the difference should be negative. We want to know these two things. All right, okay, so let's give it a go. I can use, actually, so here I'm just kind of looking what I have given. So I'm going to use this right here, which is the sum. So I'm going to use this equation right here, because I know the first and the last term, and I know the sum. So if I substitute those in, so -1442 equals n over 2. T1 is -11 plus Tn, which is -92. So I can solve for the n, so that's going to give me this, which is what I have. Now, once I have this, then I can solve for d, and I can then use, this equation or even this equation to solve for that d. So let's do that. All right. So what do we have in here? Okay, so -11, -92, you add them up. I'm just going to make it more negative. So n over 2. So in brackets, you're going to have 103, I guess, negative. So we have this, because you're going to be adding them up. And -1442 on the left-hand side. Okay, so what else do... Now I'm going to just solve for n. So from here, you can use your solution. Okay, so it's going to be this divided by -103. All right. Okay, so that's what we have there. Let's see what that gives us. So 2 multiplied by... the negatives will cancel, so I'm just going to get rid of them. All right, So that's that divided by 103, 28. Okay. Okay, so we have 28 terms in here. So that's 1. Now finding the difference between them. So I'll use this one. I think this one is easier now that I know n. So Tn is 92. I'm just substituting it back in. T1 is negative 11. I don't know the difference. N is 28. So 28 minus 1. So again, now I can just solve for D. Okay, so let's do that. I'll bring this over to the other side there. Okay, so let's go ahead and do that. So negative 92, so plus, it's going to be 11 because as it switches over, so we have that. And then once you bring that over, so you're going to really get, so this is 27D, right? So you can divide both sides by 27. So I can take this answer divided by 27, that's negative 3. Okay, so that's your difference. So it is negative, it just keeps decreasing. So there we have it. So that was question number 1. Okay, let's take a look. So question number 2, plot the above sequence using a graphing tool, identify the domain and the range. Okay, so whatever graphing tools you guys use in class, as you know, in all my video series, I pretty much always use Desmos. So I'll pop up Desmos in just a second, but now let's maybe define the domain and the range, okay, for this, and plot the both sequence. Okay, so we're plotting the sequence itself. So now that we know all of this, and this is going to be for, question number 2. So our sequence, so Tn, I mean, if you like, you can write it as a function, right? So f at n. T1, so T1 was negative 11, it's going to be minus 3, okay, and minus 1, so that's what we will have there. So we can plot it like this. I mean, you can simplify this as well, just so that it's really, because what it's going to be a line, right? It's going to start at negative 11, and then it's going to keep going down, except it's a sequence. So let me just simplify this. Negative 11 minus 3n plus 3. So grouping these two things together. Okay, I'm going to rearrange it so it kind of looks like a line. So negative 3n minus 8. Okay, so that's what we have. So if you wrote it out as a function, it's going to be like this. Now the domain. So for the domain, I mean, it's so basically the domain. So n, well, it's an integer, a natural number, right? So that's what we have there. There's now it does actually end, so I have to be careful here. And so it's n, so it's natural number, and it goes from so it's 1 and ends at 28 because we have 28 terms. All right, so that's your domain. Now the range, okay, so if you're defining your range, so this is a little bit trickier, okay? So for the range, so we know, so it's because it's points, right? So it's not like your continuous functions where you can just write down and it's everything. So we do have to be careful a little bit here. So this is, it's going to be Tn, okay, whatever that is, such that, and then we just define our Tn. So it's going to be 3n minus 8. This is actually a good exercise for you. Sorry, let me define. So here, where Tn is equal to, so I'm going to just literally write this out because that's our, it's going to be our range because it's only at these points for n, and in a natural number, and so so the range is a little bit harder to define because it's only for those values of Tn, right, that we will have for this particular thing. Okay, so now let me graph it. Okay, so I'll pop up Desmos. All right, so in Desmos again, so just for plotting sequences, you know, so you can, so the way that you will define this, so this is going to be, you know, a range n like this. All right, n we're setting to 28 because we want 28 elements. We're going to define, okay, so this, you have to define this function first, so negative 3x minus 8. I think that's what it was. All right, now I don't want to, well, actually let's show this. And now to plot it, because you want it for the n elements, so I'm just doing the ordered pairs and I'm substituting the n for here. All right, so I mean it's going to be in these negative ones. Now let me remove this so that you have it. And it'll be 28, so let me, there we have it. So that's how you can plot it up. Okay, so you can kind of learn how to plot this up, whatever graphing tools. Obviously, if you're using graphing calculators or something like that, might be a little bit different. You can talk to your teachers. I just love using Desmos, so if my students, this is what they would be utilizing, you might as well come to the 21st century, right, for these things. All right, so that's the graph for it. So that was question number 2. Okay, let's keep chugging away. So question number 3. So let's see. Expand. All right. So this kind of reminds me in this chapter. So expansion. It's funny because when students do this, they literally actually expand most of the time. So they'll do this. You know, and then they'll just continue. So they'll do the distribution and then they keep multiplying, you know, and then again, and then trying to collect like terms. I mean, you can do it, but it's torture, right? So the point of it is in the sequences and series chapter, you know, you should kind of probably remember Pascal's triangle. And so that's going to make things a lot easier for you. So within here, you know, this is to the 4. And so basically what happens is if you remember Pascal's triangle, then it makes your life a lot easier, okay, in order to expand these things. So I'll just do a recollection of that. So Pascal's triangle, so you start with 1, and then what you're doing is, you know, you are just adding up, you know, the values as you go along. Okay, so in here, so this is going to be 1. Now if you add these 2, this is going to be 2. Okay, this is going to be 1. Again, this is 1. Adding these 2, that's going to be 3. Okay, so this is 3. This is 1. And so by the way, so this is your first order. Okay, this would have been your second order. This is your third order. Now we want fourth order. So if I keep going, so 1, so these 2 added, 4. I think you get the gist. This will be 6. This is 4, and this is 1. All right. So this is now fourth order. Now, if they torture you and tell you fifth or something, you can continue with this triangle. So this is what makes it a triangle, because it just keeps going in kind of that direction. Let me remove. And what you're doing is you're just adding those up. All right. So that's Pascal's triangle. Now you can use that, and what that means is these are your coefficients. All right, so let's do that. And then, so what you have is, this is term 1 plus term 2 to the 4th. Okay, now your term 1 here is 3z. Your term 2 is negative 4. Okay, so I'm going to keep it like that. And now, in terms of expanding it out, okay, so trying to get the whole thing, so it's going to be, so term 1 to the 4, so this is 3z, okay, to the 4. Now, it's going to be plus, okay, so you're going to take the coefficients, so you take the coefficient 4 from Pascal's triangle, and then you have, so 3z, which is your term 1, it goes down in its exponent, so it goes to 3, and then your negative 4 is going to be 1. So plus, now again, so you're going to take this, so 6. This is now going to be 3z. This goes down again 2. Negative 4 is 2. So notice the term 2 increases, term 1 decreases. Now we're going to run out of space here. So I'm going to shorten this out and shift it. All right, so this is what we have. Next, so I have that. So 4, term 1, so 3z, now it's to the 1. Negative 4 is now to the 3. And finally, the last one, coefficient is 1. And this is going to be negative 4 to the 4. So that is your whole thing. You know, if you're running out of time on your test, you can just put that and just say ... and try to expand it or simplify. I'm not sure. Here they say simplify. So I'm going to just do it in fast forward fashion. I'm just going to, apply the exponents onto each factor and then add like terms. Okay, so let me do that in fast forward fashion for you. All right, so welcome back. So here you go. You can kind of double check for yourself. So notice z to the 4th or z to the 4th, z cubed or z to the z cubed, z squared, z, and then nothing. And there you have it. Okay, so that's expanded and simplified using this. If you had to do it, and do it this way, it would take you a long, long time. Okay, let's take a look at another question. So question number 4. Okay, so we have this. Let's see what they ask us here. If you know that r is equal to 1, where r is the ratio between terms in the geometric sequence, then what is the general formula for the series? How about if r is equal to negative 1? Okay. So this is actually sometimes a common question, because if you notice, so if I go back to the geometric series here, so if I go back to here, right? So if I have this, so copy, let's take a look, paste it. For the series, okay. So if r is equal to 1, we have a problem, right? Because this is actually not defined for 1. Because it's going to give you 0. So 1 minus r is going to give you 0 in the denominator, and so really we don't have a sum. But if r is equal to 1, that doesn't mean the sum is actually equal to 0, right? So let's take a look what happens. So if r is equal to 1, let's see what the formula would look like if you just had this. So you would have your term number 1, right? Now what does this mean for term number 2? Well, r is equal to 1. So if the ratio is equal to 1, so that means term number 2 is also equal to term 1. Term 3 is also equal to term 1, okay? And so on, all the way up to term n. So really what we have is we have t1 plus t1 plus t1, okay, and so on. So we have this, and how many of these do we have? We have n of these, right? So the formula, so Sn, is equal to n multiplied by t1, because that's how many of them you have, right? And this is for assuming r is equal to 1. So that would have been the actual formula. And clearly, if we used this for r is equal to 1, it just won't work, because our denominator is going to be 0. So that's why the formula is that. Now, if it's negative 1, well, if it's negative 1, then it's not a big deal. Okay, because if it's negative 1, we can just go back and actually use this. So if I copy this, let me bring it down. Now, the reason why I say it's not a big deal, because I can substitute, so t1, 1 minus, okay, so negative 1 into here, okay, and I can substitute 1 minus negative 1 into here. So notice in the denominator, what you will have is 2. So this is going to be t1 over 2, and this is going to be 1 minus Now here, we're going to have to be careful, right? So it depends what n is. If n is even, so if n is even, right, then this term right here, if it's even, it's going to be equal to 1. So what you're going to get is you're going to get t1 over 2, 1 minus 1, which is going to be 0. So that means your sum is 0. That shouldn't surprise you, because what you really have in your sequence is you're going to have a term t1 and then term t minus 1, t1 minus t1. So if there is an even number of them and you try to add them up, they're going to just sum up to 0. Now, if it's odd, if n is equal to odd, then what will happen is, so that term, so this term, if it's odd, it will actually be negative 1, right? So if that happens, so you're going to have t1 over 2, okay, because that's the denominator there. And then you're going to have 1 minus negative 1. So this also becomes 2. So the 2 will cancel with the 2, and this is just going to be t1, right? And again, that shouldn't surprise you, because what will happen is you're going to start with t1 like this, okay? Now, assuming like whatever t1 might be, and then you're going to have an odd number of these, right? But all of these, again, are going to cancel each other off. And then you're just going to be stuck with that first term. So that's a pretty good exercise for students to think, and to provide these. So that means for n is even, you would say it's 0, and for n is odd, it's t1. But you probably have to show this to your teachers so that they know where this is coming from. All right? Okay, so that was another question. All right, so let's take a look at question 5. We have, this one hopefully is a little bit shorter than the other ones. So we have, so find the sum of the sequence. So basically we're finding, looks like it's a geometric series, okay, because we're finding the sum of it. Now, if it exists. Now, does it exist? Well, so if you recall, so for the geometric series, so the sum, so Sn was equal to, and this was t1, so whatever you're starting off with, and it was 1 minus r to the n all over 1 minus r. That's how I remember it. Now, just from the previous question, so r is not equal to 1, but if we find that the magnitude of the ratio between the terms is between 0 and 1, then we know that this series exists, okay? And this looks like it's an infinite series because they say dot, 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 so they didn't stop. Which sometimes, what students will do is they, find the sum. They'll just take these 4 terms and they'll give me the sum. Now, don't forget that it says dot, dot, dot. That means it keeps going forever. So if it is going forever, so that means we're finding, this at infinity. And we just have to make sure that the ratio is between 0 and 1. And if it is, then we're good to go. So it looks like r is going to be what? Negative a half, I think, right? Let's just make sure that all of them, yeah, so you have, so negative 19 over 2, right, divided by 19, okay, so it's going to be like this, so it's going to be negative a half, and if you take the next, so 19 over 4 divided by negative, so this is going to be this. All right, so that cancels, that still is negative a half, yeah, so that's what it looks like. Okay, so r, in this case, is equal to negative 1 over 2. So let's find it out. So that means, so this thing, so r to the n, is, so when you have this to the n, and this goes on to infinity, You know, so we talked about this in one of the videos. So this basically goes to 0. So that term is going to be 0. So our sum is just T1. So that's in the numerator. So that's 19 divided by 1 minus R. Now R is negative a half. All right, so it's that. This is going to be 19 all over. And so that's going to be 1 plus a half. So this is 19. This is, I guess, 3 over 2. Which equals to 38 over 3. And there you have it. So that's going to be your sum. All right? So it's going to sum up to that. So it very quickly kind of dissipates down. Okay, great. Let's take a look at another question. So what do we have there? Question 6, find the sum of the sequence. Okay. We have this, copy. This looks like an arithmetic one. Okay, we don't know how many. Okay. So we know our term 1. This is our term n. The difference here, the difference looks like it's minus 3. Okay, so it's not a geometric. So this is in the arithmetic sequence. And if we want to find the sum of it, so basically the series, well, I mean, if I know this, I guess I don't know how many terms I have. Okay, so let's find the number of terms in here. Okay, so Tn, again, is equal just to T1, you know, plus Dn minus 1. So we know that. And if that's the case, so I do have D, I have Tn, I have T1, I have D. So I can find n. So let me do that. So negative 73 equals negative 1. This is minus 3. Okay, n minus 1. So I have this. Let's solve for n. Okay, so I'll just solve for n in here. Let's do that quickly. All right, so n is 25. So now we can find the sum. So Sn. Now, because I have the first and last term, so I'll just use this formula. So T1 plus Tn. It's negative 1 plus negative 73. All right, and then we can find our sum. So 25 over 2, so it's going to be negative 74. Okay, so let's do it. All right, there you have it. Okay, so that's the sum. Okay, let's keep chugging along. What else do they have here? No. Fibonacci sequence, very nice. Okay, so this is a little bit torturous, you know, for those students who don't know how to do this. So the Fibonacci sequence is always Tn is equal to, so this is kind of recursive, right? We need to know Tn minus 1 plus Tn minus 2. And now in this case, they're starting, so this is T1 is equal to 1 and T2 is equal to 1. All right, so this is for n. Is a natural number, but n has to be greater than 2, right? So for 3, 4, and so on. So notice so T3 is going to be 1 plus 1, right? Because it's T1 plus T2. T4 is going to be 1 plus 2, okay, which is 3, okay, and so on. Now the problem that here is, if they ask us for the 100th term, I I mean, I guess if you were given enough time, you can just keep going and adding and adding and adding and adding. But they do say approximate. So the key thing is for this Fibonacci sequence, you may remember, I'll put a link up above there, okay, to that video on Fibonacci sequence. You can actually approximate. So after a while, the Fibonacci sequence gets closer and closer to a geometric sequence where there is actually a ratio. You don't see that in the first few terms, but you do see it a little bit later on. So for instance, so if I rewrite this, so we have 1, 1, 2, 3, 5, 8, then it goes 13, right? Then it goes 21, and so on. So if you remember, for the geometric series, what you're looking for is you're trying to find the ratio in between the terms. Now, the ratio between here and here is 1, right? The ratio between here and here is 2. Between here and here, okay, it's 3 over 2, which is 1.5. Between here and here, it's, 1.6666. Between here and here, it's 1.6, all right? And it continues on. Now, after a while, let's say starting from the 21st term onwards, you will find that this ratio starts getting closer and closer to approximately, okay, 1.618. It's kind of the golden rule, okay, the golden ratio that you have in these. So for these ones, typically what your teachers will want you to do is to approximate the 100th term, just use this ratio, right? Because as you continue on, it gets closer and closer to that. So for instance, now you're not going to start term 1. So notice this is your term 1, this is term 2, term 1, term 2, term 3, term 4, term 5, term 6, term 7, term 8. All right. So what you're going to do is you're going to say, okay, starting like if your term, term number 1 was 21 onwards, then you take the ratio as approximately 1.618. And if you have that, then remember from the geometric sequence, we can find, so this was just T1 R n minus 1. Now, of course, this n, okay, right here, you have to be careful because don't plug in 100, because if you plug in 100, that means you will actually find more terms because you're skipping these terms right here, right? So let's say I started from 21. Now you can start at even 13. It would still give you a pretty good approximation. So I think your teachers would still, what they want to see is they want you to notice that eventually the Fibonacci sequence starts to being approximated by a geometric sequence that you have, right? So I'm going to remove this. Okay, so I don't want, okay, so T1, T2, T3, 4, 5, T7, okay? So my T1 really is 21, okay? My R is going to be approximately that. And now, so since I left off, okay, 7 terms, so I'm going to say, so let's say 93, okay? I'm finding, starting from 21, so 21, right, is the 8th term, okay? And then, so let me just do this correctly. So term 8, okay, let's say term 9, term 10. So let's say if you wanted to find the 10th term, okay, and this was your first term, then this would have been, so let's say this was term 1, term 2, okay, let's say term 3. So that means, yeah, so you're basically subtracting the 7 first terms if you wanted to find the 10th. So it would have been to the 3. Correct. So we would have said this is 100 minus the 7 that we removed. So it would be 93 minus 1. That's from the formula. And now we can approximate it. It's going to be 21 times 1.618 to the 92. That was going to be pretty big. Whoa. Okay, it's enormous. So this is scientific notation. And of course it will be, because look at the exponent. So maybe you know, let's kind of, so I'm going to write it in scientific notation. It makes sense that it's enormous number. So it'll be something like that. All right. So approximated by about that much. All right. And now actually what I'll do is I'll kind of look it up. I'll Google it up. I want to see what the Fibonacci sequence, okay, is for the first 100 terms. So they factored it out actually. So it would have been 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, so 20, yeah. So I'm looking at the 100th term right there, and I was just counting how many, because if it's in scientific notation, what it would be. So notice it's 3.5422. That's the exact one that they put there. And 3.53387. Again, we're approximating because, you know, that ratio is not exactly 1.618. You know, it's not exactly that, but this is how you would kind of tackle this question. So I hope it gives you an idea, and that was the main goal of this question. Okay, keep chugging away. All right, okay, so for the last two questions, I've actually decided to, when I was working on this test, I decided, you know what, let me make separate videos on both these two topics. So tying in the arithmetic sequence to the simple interest, and then tying in the geometric sequence to the compound interest. All right, and I did kind of separate videos, and I did actually, at the end of those videos, these two examples there. So I'll refer you to there. So I'm sorry, it's not self-contained. So for the first one, arithmetic sequence, you know, and tying it into simple interest, I'll put up a link up above there for you so that you have it. And, you know, for the second one, which is the compound interest, tying it into the geometric sequence. So, you know, I'm basically just, so that's what it's kind of going to look at. Okay. I'll put up a link up above there. All right. So that you have both, and then you can take a look. Now, if you want to just know what the answers were, so the answers I did actually kind of right here. So it was 39,000, okay, for the simple interest question, and then it was 69,914 and 36 cents for the compound interest. But I do the explanations and the whole derivation and tying them in together on those links. All right, okay, so this is it. In terms of sequences, all the tests for grade 11, I think I'm going to take a pretty, hopefully longer break. Kind of exhausted. I did grade 9, 10, and 11 videos, probably close to about 250 or more within probably about a year. So we'll see if I'm going to tackle the grade 12 maths in the future. All right, thanks for watching. See you in a future video. Bye, everybody. Cheers.